curves now, another type of highway design. This is in the vertical profile. So we're going to look at types, we're going to look at slopes and grades, the equal tangent curves, equal tangent calculations. Now I'll talk about equal tangent, unequal tangent curves, but we're not going to do anything with it. And if you specifically want some issues on that or answers, you can always send us emails and we'll take a look at that for you. Okay, so vertical roadway alignments contain two features, just like the horizontal do. Instead of calling them tangents, they're referred to as gradients, or vertical tangents. They're defined by a grade, percent grade, and a horizontal distance, which is typically in stations, and then they usually have defining elevations. So you usually know grade and horizontal distance, or you might know horizontal distance and elevation, but eventually you're going to kind of use all three of these things. The other thing that you would have is a vertical curve that is placed in where two gradients deviate from each other, kind of like at what we would call that PI point in the horizontal curve. It's called a PBI, but we're going to place a parabolic curve in there, and it'll either be what we call the equal tangent type or the unequal tangent type. Okay, so this is a kind of a typical example of what you'd be looking at. The green is your existing ground line. My magenta is my gradient coming in, then it's deviating from gradient 2, and then gradient 2 is deviating from gradient 3. So what we've done is we've placed a parabolic curve in here. This is a parabola, geometry of a parabola. And instead of a radius, what you're giving it is a horizontal distance from where it starts to where it ends. Okay? So that's called your vertical curve length. And then we have this kind here also. So, gradients. Gradients are defined by three elements: the horizontal distance in feet. So we never talk about the slope distance on a gradient. We don't care about that, but we do want to know what the horizontal distance is in feet or meters, or very often referenced in stations. Elevation, above or below at different points. So you can have a lower elevation, 800 to 860, something like that. And then a grade. And that is expressed in percent, feet per foot, or feet per hundreds of feet. So you could see feet per foot in some things, but not, I don't think, ever. So pretty much be looking for a percent grade kind of concept. So percent grade is basically just rise over run. So we define that as G, delta elevation in feet, divided by delta distance, horizontal distance in feet. If it's meters, then it would be meter per meter. If it's feet, it's feet per feet. But we then multiply that by 100, and that gets it into a percent. So positive G indicates you're going uphill, negative indicates you're going downhill. Now, there is no clear-cut direction the way engineers work, so sometimes they design their project from left to right, and sometimes right to left. So that could make a difference. Essentially, a 2% up and a 2% down are the same grade. It's just depending whether you're going left to right or right to left on it, okay? But 2% does mean the same thing to both cases. A 2% grade says we're rising or falling 2 feet in a 100 feet of run, horizontal run. Okay. So again, we never talk about the slope distance. That's an unknown. Not that we couldn't calculate it, but we don't care. All right. So vertical curves, the parabolas that we're going to look at, they kind of exist as one of two types, what we call crests and sags. So a crest curve is a curve that's going to kind of shield water off of it. It may develop a high point. Not all of these guys will. And it has what's called a rate of change of grade associated with it, which we define as R. That is a negative. So what that means is over time, this thing is going to trend. It may have a peak, but over time it's going to go down. Okay. The sag curve may develop a low spot, so it catches water, and it's going to have a rate of change of grade that over time is going to go positive. Okay. So this is your example. This is what you would call the classic crest curve. Notice my G1 is coming in positively, G2 is going out negatively, and this thing is somewhere along here developing a high point. Okay, and it's not always right opposite the PVI, by the way. It would depend on what the values of the G1 and G2 value are. Sag, this is a classic one that's going to catch water down here somewhere. G1 down, G2 out, up. Okay. This is going to be your classic, what we would call sag. Okay. So parabolic curves have 6 defining elements, like we had 8 in the horizontal curves. So we usually have a G1 grade, that's the grade coming into the curve. G2 is your grade going out, so that's sometimes referred to as your back tangent, forward tangent, or gradient, probably is a better term. Length of vertical curve, L, remember that is the horizontal distance, okay, of that curve. Algebraic difference is the difference between the two grades, so literally you're just subtracting grade 2 minus grade 1. That's right. That would be analogous to delta in a circular arc. Rate of change of grade is the amount of slope change that this thing is happening as you're traveling along your parabola. Okay, that's going to either, again, as we said, either have a positive or a negative number associated with it. And E is what's referred to as your vertical offset. I'll show you here in this diagram what that actually is. Used less often. Vertical curves are going to have significant stations associated with them. 3 primary ones. The beginning of the curve, BBC, PBI, point of vertical intersection, and EVC is your end of vertical curve. Some people use the terms PVC for point of vertical curve and PVT for point of vertical tangency. Some people even call these PIs, but I think that's a bad way of thinking that because we think horizontal PIs and they're not the same at all. Alright, so this is a schematic of what we're looking at, of the different elements. So this is the grade coming in, grade going out. This is where they're meeting at the PBI. So this grade would be a positive G1, negative G2. Okay. Notice our parabola is starting at the BBC. It's represented by this red curve right there. That's ending at the EVC. So the length of this thing from the BBC to the EVC, this is the horizontal distance. So that would typically be given in stations of feet. So notice also, this is called an equal tangent parabolic curve. So what that means is that it doesn't mean this distance and this distance are the same. You can clearly see they're not. But what it means is if we drop this vertical line straight down, it bisects L, so what you have is L over 2 here and L over 2. So there's your reference to that concept of vertical equal tangent. Notice also we can draw a line from the BBC to the EVC. That's your chord of your parabola. If we take that bisected line and we look at this, if we drop that distance from here down to the parabola, that's E. And from that point on the parabola to the chord, that's also E. So these are always equal in parabolas. That's one cool thing about them. We don't use that too much, but that's there. So then if we're gonna solve any point on this curve right here, we need to know the distance we are from the BBC out to that point, and that's defined as value x. Okay? So one thing too, as we get into this, these guys are expressed in percents. These guys are expressed, that guy is expressed in stations. X is expressed in stations, and these are going to be in stations as well. Okay? So here's your key equations. Algebraic difference is grade 2 minus grade 1. So that is important because you have to consider the sign of both of these. So if you have a negative minus a negative, this is going to become a plus grade, basically. So you got to watch that. The rate of change of grade is your algebraic difference divided by L, where L is expressed in stations, or you can just do it grade 2 minus grade 1 divided by L. The actual equation of parabola, so any value y, which is actually the elevation on the curve, is going to be r over 2 times x squared plus g1x plus BBC elevation. So once we have calculated some of this stuff, it's just easy to plug it in, and what this allows us to do for any value x, we can get a value y on that parabola. So here's an example. We're going to look at solving this thing for this parabola. We've got a positive grade coming in, a negative going out, a length of 600, and a PBI station and elevation. So we're going to solve the BBC, EVC, and we're going to solve the equation of parabola and some of the stations along that. Okay, so here's that problem we were just looking at. We're given a grade in, 1.25% and a grade out. So I like to draw a little sketch. It just kind of relates them. Looking at this also determines whether you got a crest or a sag. So it's really helpful. PBI, station elevation, and we know L. So we're looking at that. So what we need to do first is solve BBC and EVC. So this would be my BBC location. This is my EVC location. By the way, I know that, by the fact that this is G1 and that's G2. Okay? So that's what interrelates those. So for the equation of these, it's pretty straightforward. The BBC station is going to be equal to the PBI station minus the distance from here over. So since this is an equal tangent curve, it's just going to be half of 600. So you could take L and write it in an equation like this, just divided by 2. So we're taking 300 feet and subtracting that, so we get 15 plus 0, 0. So the BBC elevation is going to be equal to the PBI elevation, which in this case is 886.10. So if you notice, we're dropping, okay? So basically what I'm saying is I'm going to go negative, subtract, whatever my grade's giving me. Now, so my grade, 1.25, that's in percent, times the distance over which I'm going. So the grade times the horizontal distance will give me the rise or fall. Now, if you express this in percent, which I am, then I'm going to express this in stations. So 6 stations, 6 feet, 600 feet is 6 stations. So in our case, we're 300 feet, so this would be 3 stations. So what's happening in that picture, what a lot of people do is they'll add that because that grade is coming in as a positive, and by doing that, of course, you went the wrong way. So the picture is very helpful in this case. And so what you do is you come up with, this has to be lower elevation. And I'm coming up with 882.35. Okay? So we're going to reference BBC, or EDC, excuse me. EDC works out very similarly. So that's going to be equal to the PBI plus, in this case, half of L. So we're adding, in other words, 300 feet to that. We're getting 21 plus 0, 0. Now normally also, what's nice about vertical curves, you'll notice these are really nice stations, all of these. Where horizontal curves are not typically, because it's hard to do that. So with a vertical curve, it's very easy to do this if the designer is really good. If you're getting things where the designer's not doing that, he's not a very good designer. So that would be my opinion. So EDC elevation is going to be equal to the, again, PBI elevation. And we're going to, this time, we're going to add the difference, but we're going to let the grade do the work. So this is a minus 2.75, okay? So 2.75%, again, over a distance of 300 feet. So we're going to convert that to 3 stations. And again, by that picture, it looks like it should be dropping, and it is, and it's dropping at a larger rate than the other one should, so it should drop further than this. When I calculated mine, you guys can verify this, we get 877.85. Okay? So, what we now can calculate is the R value that relates this stuff all together, the rate of change of grade. The rate of change of grade, R, is equal to G2 minus G1 divided by L. Now, this is what we call a crest curve, so it's going to have a negative R over time. So we should expect a negative value. If you don't get that, you did something wrong, so always be aware of that. Crest is going to be negative, sag is going to be positive. So G2 literally is a negative 2.75, and we're going to subtract from that a positive 1.25%. So you can see that's going to clearly give me the negative signs right there. That establishes that. Then we're going to divide this by L, but instead of doing it in feet, you do it in stations. So this will be over 6 stations. So what we're going to do is we're going to come up with a negative 6.667. I usually float that out a little bit because that gives me better quality when I do my calculation. So we're ready now to write the equation of parabola. The equation of parabola generically says y is equal to r over 2 x squared plus g1x plus BBC elevation. So we're literally just going to plug things in. So we're going to take this guy here, over 2 times x squared plus g1x. G1 is this guy. He brings his sign with him. So if he was negative, you'd have a negative value there, but in this case I have a positive value, plus the elevation of the VBC. VBC, we add to that 882.35. So there's my equation of parabola. Now this equation is good for any parabola infinity, negative x to negative positive x, but this parabola is only good for the range over which we're looking at it, which is between here and here. So if you want to say this is nice to look at. This parabola is only good from 0 to 6. So you really can't put a value less than 0 in there or greater than 6, because it's not going to be, you're going to be out here on your tangent and your parabola is going to be down here. Okay, so there's going to be a difference. Okay, so everybody, what we see here is 0 to 6. So one way to check this parabola equation right now is to plug 6 into here, and I'll always do this as a check. If I plug 6 into this equation, what I should get out of here is what I calculated on the tangent at 877.85. So plugging 6 in, we're going to square it, take it times that, we're going to take 6 times that, and just do the math, and what we'll find out is by doing that, we're going to get this, and I just did that, and that checks. Okay. So any value that you would want on your parabola, you have the ability to get now. So if you were told that you wanted to get this station right here, and let's say you're told this station is at 19 plus 0, 0. We want to know what the elevation of that is. All we would need to do is calculate this value of x. So x in that case would be 19 minus the VBC, which is 15. That gets us 400 feet. Dividing that by 4, or 100, gives us 4 stations. So we would plug 4 stations into here, and that will give us the elevation of that parabola. So to do that, all right, so taking, if we wanted that station, we just subtract from the VBC to where we want to go. That gives it in feet, convert it to stations, plug the stations in, and when you run the equation through, this is what you're going to come up with for that. So that gives you the elevation of the point on the parabola at that point. So you can literally just go any point you want on that parabola. Okay, so the other thing that you have in vertical curves is the development of either a high point or a low point. So high points are going to be associated with crests and low points with sags. Of course, it's very important because a crest is where you're going to sheet water off, and a low point is where you're going to catch. So that's an important location, probably more than anything, because that's where you're going to have to place catch basins. The location is in terms of station, and the elevation of it has to be determined, and that's pretty simple. Now, the one thing about this says that you can get a high point and a low point on sags and crests, but you don't always get that. And the reason is if the grades don't change algebraic sign, you will not get a grade. You will not get a high point or a low point. So if you go from a positive value G1 to another positive value G1, you're not going to have a high point or low point. That's what that's saying. So the simple equation is to calculate the value of x first, and then just plug it back into your parabola equation to get your value. So this will get me station, and the other thing will get me elevation. So there's 2 ways to do it. You can take negative G1 divided by R, which is very nice, or you can take G1 times L divided by G1 minus G2. So these are the same equations. It's just, if you have R already at your disposal, it's just real simple. So we'll take a look at the high point on the last problem that we just did, and we'll take a look at that. Okay, so looking at the last problem, we calculated the parabola, calculated the key points. But the one thing we didn't get was the high point or low point. Well, this is a crest curve, so it would have to be a high point. And you're definitely going to get one to develop because we're going from a positive grade to a negative. So we know that we're going to get a high point. Somewhere along here, we don't know where it is. Now, a lot of people assume it'll be right there, and that could be true, but the only way that's going to be true is if these grades were the same numeric number. So if you were 2% in, 2% out, yeah, it's going to be there symmetrically. But since it's not the case, it's going to push it one way or the other, the PBI. So we're going to determine where that is. We're going to use that equation. We said we had that equation. Let's say we had G1 over R, negative G1 over R. We can use the other equation that we had to calculate that. So we need R, and let's calculate R first because I already had that, but we'll do that again. So that R is G2 minus G1 minus 2.75 minus the 125 divided by L in stations. That gives me that negative 0.0667. Okay. So in this case, if we're solving that, we have G1, which is a positive, so that's going to go at negative 1.25 divided by a negative 0.6667. So it's good that we have negatives on top and bottom because what that's indicating to me is I'm going to get a positive number. X has to be a positive number because it can't be outside, it can't be negative, it can't be out of this. And it can't be greater than 6. So if we get a number that's negative, or we get a number that's negative, greater than 6, that's telling me you don't have a high point or a low point on this curve. At that point, it becomes pretty easy to determine. So when I do the math on this, what I'm coming up with is a number that tells me 1.875. So this is the total number of stations that we are to the high point. So we're looking at this graph here. It's saying that we are 1.875 stations from the BBC. So we would plug that 1.875 stations in for X into our equation, and again we notice that it's less than 6. It verifies what we're saying. So when we do that, our high point turns out to be an elevation of 883.52. So what it's saying is it's coming up here, starting out at 882.35, it's peaking at 883.52, and from that point on it just drops. Everything's going to get lower. So the other thing we need to pinpoint is what station it's at. So the station is actually just going to be equal to the BBC station plus X in this case. So we have 15 plus 0, 0, and we're going to add to that 187.5 feet. Because that's in stations, we have to convert that over, and we get 1687.50. 16 plus 87.50. So here's your station, here's your elevation. Okay. The last class of vertical curve that you might be encountering is called an unequal tangent. And this is composed of two equal tangent vertical curves. And they are tangent parabolas, and they're tangent at the PBI location. Okay? So you're going to have two different L's associated with this. So you're going to have a percent grade in and a percent grade out. Okay, so that's going to be like the other grade, but then you're going to have a connecting grade between the two parabolas, which I refer to as a reference as G3. You have an L value, which is the total from the BBC to the EBC, but then you have separate lengths within it. So L1 and L2 in an equal tangent are the same number, okay, just half of this, but for an unequal tangent, these are going to be different, but when you sum them together, you're going to get your L value. So you will not have an algebraic grade difference just for the whole system. you're going to have one for the first parabola and one for the second. So you actually have two separate parabolas that you're operating under. Okay? So you don't have just one unique algebraic difference. So again, common points. Okay, you really have four, although really one of them is the same. You have the PBI, which is where the two grades meet, the grade 1 in, grade 2 out. You have the beginning of the vertical curve, you have the ending of the vertical curve, and then you have the point of compound vertical curve, CBC. Well, that is the same station as the PBI. So these guys exactly share the same station, but they will have different elevations. So in this case, grade 1 in, grade 2 out, PBI. There's your L value from BBC to EBC. If I drop my vertical line, it doesn't bisect it. So you'll notice here that we have L1 and L2 then that we have. And here's your first parabola that is going from here to here. There's the point of tangency at the CBC. Again, it's opposite the PBI. And then here's your second parabola. So this is your tangent line, what we would call G3, and it's functioning between like this. So if you extended it this way, it is going to bisect this curve. Notice L1 gets bisected, and where it intersects here, it gets bisected. And we can calculate this grade really different ways. There's different ways. The easiest way is to just recognize that the BBC to the EBC, that chord, this slope is the same as that slope. So therefore, I can simply calculate this grade by the difference in elevations between these two divided by L, and I have that. And the other common parameter that you can calculate is the value of E, and then solve it. But once you get the elevation of this point and this grade in, then you have a parabola here, and what you have is functionally this G1 and this G3, that's actually G2 for this curve, and G3 for this curve is actually functionally G1, G2. So you write an equation of parabola for this guy, you write an equation of parabola for this guy, and you just handle it like we did.